Good afternoon. Hope everyone is doing good, doing well. Hopefully we can get a little bit of work done before we get back to the university. We had finished talking about signal analysis or spectral analysis. We're going to start the next topic, which is Z-transforms. We had already talked a little bit about Fourier transforms. The Z-transform is very similar, as we know all the transforms are. This is the definition of the Z-transform. So let's say we have a sequence, g of n. Its Z-transform, we write it as g of z, will be written this way. We're going to use the same notation as the book, writing functions in time with small letters, writing functions or writing the transformations in capital letters. So the definition is we take the sequence, multiply it by z to the minus n, and add it from minus infinity to infinity. Now this variable z is complex. If you remember when we were talking, or when we do Laplace transforms, the s is usually written in polar form, real and imaginary part. Z is also a complex variable, but instead of writing it in polar form, we write it in, instead of writing it in rectangular form, we write it in polar form. We write it as the magnitude and the phase. So if we have a number, let's say we have a complex number z. If we write it in polar form, r is going to be the distance from the origin, and omega is going to be the angle. Of course, zero angle is along the real line, and positive angles are in counterclockwise. Now, since this is an infinite sum, sometimes that infinite sum will be a finite value, and sometimes it will go to infinity. We really only want them when they don't go to infinity. If the summation goes to infinity, it doesn't give us any valuable information, and so we only look at it, or we're only interested in it if it doesn't go to infinity. And so we say that the Z-transform of g of n exists if the summation is not infinite. Now, this summation, of course, it depends on the sequence that we're calculating, but it also depends on z. So for some values of z, it may be finite, and for other values of z, it may be infinite. Now, what we're interested in is the values of z where it doesn't go to infinity. And we have a definition for this. And we say that the set of all values of z, where the Z-transform exists, or in other words, where it doesn't go to infinity, those values we call the region of convergence. Now, let's look at something. Right, again, we want to find the values where this is an infinite. And so if we write this, the magnitude, we know that the magnitude of the sum is less than or equal to the sum of the magnitudes, which we could write like this. Now, writing z in polar form, we separate the r and the e to the j omega. Now we know that this here, we know that the magnitude of e to the j omega n is always equal to 1, no matter what omega or n is. So we can, since this is always 1, we can eliminate it. And this, we can write it as this here, the summation of the magnitude of g times r of n. What that means is that this last term doesn't have omega. In other words, the region of convergence, the values of z, where this goes to infinity or doesn't go to infinity, does not depend on omega. It only depends on r. So it depends on the magnitude, but it doesn't depend on the phase of z. By implication, we see that the region of convergence is always a ring in the complex plane. Since it doesn't depend on omega, only depends on the magnitude, we can look at the following thing. Let's do a sketch. Let's suppose here we have the imaginary plane, right? The real axis, the imaginary axis. Let's say that we have a point, let's say this point here, and let's say that the Z-transform exists at that point. In other words, the summation is not infinite, it's finite. Now, that is going to have some magnitude. If we look at another point, let's look down here, at another point with the same magnitude, the same r, but a different omega. Now, if it's finite here, if the summation is finite here, it has to be finite here because, as we saw, it only depends on r it doesn't depend on omega. So our regions of convergence, the values where it doesn't go to infinity, are going to be circles or rings in the complex plane. So when we're calculating what values are going to be in our region of convergence, it's always going to be rings in the imaginary plane. Let's start with a simple example. Let's say u of n is the step function, right? 0 for negative values, 1 for positive values. And let's calculate its transform. Right, we just substitute u of n. Now u of n is 0 for negative values, so we don't have to go from minus infinity to infinity. The summation can start at 0, and for all positive values, u of n is equal to 1, so we're not going to write it. So we have the summation, n goes from 0 to infinity of z to the minus n. Writing this explicitly, right, this is a summation starting at 0, ending at infinity of something elevated to the power of n. Now we know what this is from our experience before. This is going to be 1 over 1 minus whatever is elevated to the power of n, in this case z to the minus 1. Now, we said that this infinite sum converges to this value if what's elevated to the value of n has a magnitude that's less than 1. In other words, z to the minus 1 has to be less than 1. Or in other words, if we solve for z instead of z to the minus 1, z, the magnitude of z, has to be greater than 1. Let's look at some other terms. One other thing that we need to define are rational functions. Now, when we're calculating z transforms, as we did here, usually we're going to get fractions. And the fractions, of course, are going to be functions of z. Now, if we can express the z transform as rational functions of z, in other words, we have a polynomial of z in the numerator and another polynomial of z in the denominator, this was what we're going to call rational functions of z. Now, two other definitions. The values of z, where x of z is equal to 0, are called the zeros of our transform. The values of z where this is infinite are called the poles of x of z. Okay. Now, if we go back to a simple example, and let's calculate everything that we've done so far. Let's calculate the z transform, let's calculate the poles, the zeros, and let's actually draw what the region of convergence looks like. So in this example, I'm saying that x of n is going to be minus 0.6 elevated to the n times u of n. Now, when we take the z transform, of course, we just substitute what x of n is here. The u of n means that the summation is going to be 0 for negative n's. So we start the summation at 0. And then we have minus 0.6 to the n and z to the minus n. So let's combine these terms so that we get something elevated to the n. And again, we have a summation starting at 0, ending at infinity of something raised to the power of n. And so we know that that's going to be equal 1 over 1 minus whatever is inside here. Now the minus here and the minus here are going to cancel out, so we get 1 plus 0.6 z to the minus 1. Now again, this infinite summation converges to this only if what's raised to the power of n has magnitude less than 1. And so we write it out like this. And from this, we get our region of convergence. These are the values of z where the summation is finite. Now, we don't leave it like this. We solve for z. And if we solve for z, we come down here and we see that the magnitude of z has to be greater than the magnitude of 0.6. Now, we can write the final polynomial as this, or if we multiply numerator and denominator by z, we'll just get z over z plus 0.6. I find it easier to calculate the zeros and the poles if we have positive values of z instead of negative values of z, but it's not necessary to do this. Now, if we look at this final rational function of z, we see that, right, if z is equal to 0, this is going to be 0, so 1 0 is at 0 equal to z equal to 0. And we look at the denominator, if we if we have the denominator equal to 0, of course this is going to go to infinity. And so if z is minus 0.6, this will be infinity, and so that's our pole of x of z. Now if we write that out in the complex plane, right, we have a real axis, the imaginary axis. Negative 0.6 is over here, and so I'm going to use x's to write our poles, zeros to write our zeros, and so we have a pole at minus 0.6. We have a 0 at the origin, and our region of convergence, we see that the magnitude of z has to be greater than 0.6. Now, if we write a circle with radius 0.6, everything outside that circle is going to be our region of convergence. And another thing, we can see that actually the region of convergence is bounded by the poles of x of z. Now it turns out that this sequence is rather general. We see this a lot. And so instead of looking at the one example as we did above, let's look at a general example. Let's say we have a to the n times u of n. We go through the same procedure as we did before. Now a could be anything. A doesn't have to be a real number, it could actually be a complex number. And so we have a elevated to the n, and instead of getting 0.6 we have 1 over 1 minus a z to the minus 1. And again, whatever is elevated to the power of n has to have magnitude less than 1. And so solving for z, we see that the magnitude of z has to be greater than the magnitude of a. And we could write it like this. And again, the poles and the 0 is going to be equal to 0, and the pole is going to be z equal to a. Writing this out, again, we can see that we don't know what a is, but assuming a is a positive real number, let me put the pole here and the 0 here. And then again, everything outside of the circle of radius, magnitude a, is going to be our region of convergence. Let's do another example. Now, I didn't mention this before, but one of the advantages of taking the class that's like this recorded is that you can pause the video. What I think is the best way for you to do it is to look at the problem, pause the video, and try to do it yourself. If you can go all the way through and finish it, wonderful. If you can't, if you're stuck at some point, start the video, go down until you get unstuck, and then pause it again and continue the problem. The more you can do alone by yourself, the better practice it will be. So now this is a different sequence. Okay, we have minus a to the n, u of minus n minus 1. When we substitute that in our summation to get the z transform, right, the negative value can come outside. We'll have a to the n z to the minus n. Now this u of minus n minus 1, we have to see where it's 1 and where it's 0. Make sure you can do this. Now it turns out that if n goes from minus infinity to minus 1, these values will be 1. And if n goes from 0 to infinity, these will be negative. So the values that are 0 in our summation are the values from 0 to infinity. So our summation is now going to go from minus infinity to minus 1. Now, instead of having negative values here, I would rather have positive values. So let me change n for negative n. And so I'm going to change this minus infinity to plus infinity, minus 1 to 1, and then the minus n's, the n is going to be minus n, and the minus n here is going to be n. And so this summation, a summation from 1 to infinity, of course, then we can solve it. Writing this explicitly as a to the minus 1 times z elevated to the power of n, we know how to write this summation. Right, this is going to be a to the minus 1z over 1 minus a to the minus 1 times z. The negative value is still there. Again, this isn't for all values of z. So this is for values where what's inside the parentheses has to have magnitude less than 1. If we solve for z, we see that in this case the magnitude of z has to be less than the magnitude of a. Now, one thing, let's take this fraction and play with it, right? If we multiply numerator and denominator by a, we'll get this thing here. And if we eliminate this negative, right, we'll change the signs of the two values and we'll get the same fraction that we had for the previous example, right? Now this is an important point. This sequence and the sequence of the previous example are not the same. This turns out to be the same. The difference, of course, is the region of convergence. So it's important that we write this down. Now the poles and the zeros are exactly the same as we had before, of course, because the rational function is the same. And so we write it like this. Now, the region of convergence, as I just mentioned, is magnitude of z less than a. So the values of z inside this region of convergence is now going to be inside a circle that has radius a. And again, let me emphasize this. The last two examples have almost the same transform. The only difference is the region of convergence. You must specify the region of convergence when you calculate a z-transform, okay? And the exam, if I tell you calculate a z-transform and you don't write the region of convergence, if you only write the fraction, it's going to be half right. You'll get half the points. So make sure you write the region of convergence, right? And to drive that point home, if they give us an x of z and they tell us it's this, and they tell us find the inverse transform, because we're going to do that later on, we don't know if we should inverse this as the first sequence or the second sequence unless they give us the region of convergence. So let's do one final example. Okay, let's say in this example, we're not going to have a step function. It's just going to be alpha to the absolute value of n. In this case, alpha, although I didn't write it down, we're assuming that alpha has magnitude less than 1. And let's calculate the z-transform of this. Again, pause the video, try to calculate it before we go on. So, this is the definition of the z-transform. Let's substitute x of n here. Now, we need to get rid of the absolute value on the alpha. And so, of course, we need to separate this infinite sum into values where n is negative and values where n is positive. Right? Where n is negative, we can just write this as alpha to the minus n. And where the n values are positive, we can write alpha to the absolute value of n as simply alpha to the n. And so we have to calculate, or we have to evaluate two infinite sums here. Now, the second infinite sum, let's just write it the same. Now, this one, again, as I did in the previous example, I don't want to work with negative values of z. I'd rather work with negative values of n. I would rather work with positive values of n. And so let me change n for minus n. And so here we're going to go from 1 to infinity, alpha to the n, z to the n. And again, although I had talked about this before, let me comment. Here the summation goes from minus infinity to minus 1. Now, if this summation converges, it will converge, doesn't matter what order we're going to do the summation. So I can invert the order of the summation and it's going to give me the same result. Now this first summation that goes from 1 to infinity of alpha n z to the n, of course, is going to be this, alpha z 1 minus alpha z. And the second summation is going to give us this second term here, as we had done before. Now, each of these terms has its own region of convergence. For example, the first term is going to converge if alpha times z has a magnitude less than 1. Or if we solve for z, z has to have a magnitude less than 1 over the magnitude of alpha. The second term, we need alpha z minus 1 to have a magnitude less than 1. Or again, solving for the magnitude of z, we need it to be greater than the magnitude of alpha. Now, if we simplify this, let's take this down here and simplify our fraction, just to put it put it in terms of one fraction instead of two, we get this final term. And in here we can easily find, or relatively easy, we can find the zeros in the poles. Looking at the numerator, we see that it has a 0 at z equal to 0. And if we equal the denominator to 0, we see it has two poles, right? Since the denominator now is a polynomial of second order, it's going to have two poles. And so z equal to alpha and z equal to 1 over alpha are going to be our poles. Now, how do we find the region of convergence? Now, for x of z not to be infinite, we need both sums, or both of these infinite sums, to be finite. If one of them goes to infinity, x of z is infinite. And so we need both of them to converge. So the region of convergence, we need both z to be less than 1 over magnitude of 1 of alpha and z greater than alpha. So we need both summations to converge, and so we need both conditions at the same time. And so the region of convergence is going to be the first condition and the second condition. In other words, if we write them both together, it is just z between the magnitude of alpha and the magnitude, or 1 over the magnitude of alpha. If we write that, if we draw the pole zero diagram and we write the region of convergence, it'll look like this. I didn't write the pole, I didn't write the zero at the origin, but we have two poles, right? Alpha and 1 over alpha. As I mentioned, we're at the beginning of the problem, alpha is going to be less than 1, so 1 over alpha is going to be greater than 1. And so we have alpha and 1 over alpha here. And we know that the region of convergence are values of z between those two extremes. A circle of radius alpha and a circle of radius 1 over alpha. Homework problems for you to practice on. First, I want you to calculate various z transforms, and don't forget the region of convergence. Also, I want you to do problems in the book 2, 3, 5, 6, 7, and 14 from chapter 6. Let me know how this goes. If you have any problems, write to me. We'll see how this works out.